Transformer principle. It is a device that works on the principle of electromagnetic induction. It converts alternating current at low voltage into high voltage and vice versa. Here, two types of transformers are shown. This is soft iron core. Here, this is also soft iron core. Here, this is primary coil, this is secondary coil. In this case, primary and secondary coils are one over other, and this is soft iron. Now, let's see construction. A transformer consists of two sets of coils insulated from each other. They are wound on a soft iron core, either one on the top of other or on separate limbs of the core, as we have seen in the two cases. One of the coils, called the primary coil, has n1 number of turns, or we can also denote it as np, and the other coil is called the secondary coil, having n2 turns, or sometimes denoted as n2, sorry, ns secondary. Now, let's see the working. When an alternating voltage is applied to the primary, the resulting current produces an alternating magnetic flux which links the secondary and induces an EMF in it. The value of this EMF depends on the number of turns in the secondary coil. Now, we consider an ideal transformer in which the primary has negligible resistance and all the flux in the core links both primary and secondary windings. Let phi be the flux in each turn in the core at time t due to current in the primary when a voltage V1 is applied to it. Then the induced voltage or induced EMF E2 in the secondary coil with turns N2 is given by E2 equal to minus N2 d phi by dt. Suppose this is equation number 1. The alternating flux phi also induces an EMF called back EMF in the primary. This is given by E1 equal to minus N1 d phi by dt. But E1 means induced voltage is equal to applied voltage, and if secondary coil is open, in that case, or if secondary circuit is open, in that case E2 equal to V2. So we can write V2 equal to minus N2 d phi by dt and V1 equal to minus N1 d phi by dt. So if we equate the value of d phi by dt from these two, we will get V2 divided by V1 equal to N2 upon N1, or V secondary divided by V primary equal to number of turns in secondary divided by number of turns in primary. Now, if the transformer is 100% efficient, then input power and output powers will be equal. So we can say I1 V1 means input power equal to I2 V2, that is output power. So now from here we can find the value of V2 upon V1. So if we find V2 upon V1, that will be V2 upon V1 will be equal to I1 upon I2. So we can say V2 upon V1 equal to N2 upon N1 equal to I1 upon I2, or voltage in secondary divided by voltage in primary equal to number of turns in secondary to number of turns in primary equal to current in primary divided by current in secondary. Now, there are two types of transformers. Number one, step-up transformer, in which number of turns in secondary are larger than number of turns in primary. So NS is greater than NP, or N2 is greater than N1. Step-down transformer, here number of turns in secondary are less than the number of turns in the primary. So NP is greater than NS, or N1 is greater than N2. Now, efficiency of a transformer. Efficiency eta is given by output power divided by input power. So power equal to P equal to VI. So voltage in secondary times current in secondary divided by voltage in primary times current in primary. So only ideal transformer can be 100% efficient. So it means there is always some energy loss in the transformer. Let's see all types of energy losses in the transformer. So energy losses in transformers are number one, flux leakage. There is always some flux leakage. That is, not all of the flux due to primary passes through the secondary due to poor design of the core or the air gaps in the core. It can be reduced by binding the primary and secondary coils one over the other. The first figure, as we have seen. Second point, resistance of the bindings. The wire used for the bindings has some resistance, and so energy is lost due to the heat produced in the wire according to the formula I square R. In high current, low voltage winding, these are the minimized by using the space here, thick wire. When thick wire is used, in that case, this loss, resistance loss will be less because resistance is inversely proportional to area. Next current. Next thing is eddy currents. Due to eddy currents, there is loss. The alternating magnetic flux induces eddy currents in the iron core and causes heating. The effect is reduced by having a laminated core. And last one is hysteresis loss. The magnetization of the core is repeatedly reversed by the alternating magnetic field. The resulting expenditure of energy in the core appears as heat and is kept to minimum by using a magnetic material which has a low hysteresis loss. Thank you for watching.